This is the second video for section 7.2, graphing rational functions. In the first video at the end, we talked about simple translated functions. In this video, we're going to talk about, you can call it, quote, advanced rational functions. And advanced rational functions have the form that you see on the screen there. Y equals ax plus b over cx plus d. Now, with these advanced rational functions, we're still going to have a vertical asymptote and a horizontal asymptote. Okay, but the way we find them is just slightly different. The vertical asymptote, since it's a vertical line, it's going to start with x equals, and how we find it is we're going to take negative d and divide it by c, or you can just put this negative sign out front. I'll do that here. Negative d over c. So whichever one you want to make negative, that's fine. Or if you just want to do d over c and throw a negative sign over top of it or out front of it, that's fine too. For the horizontal asymptote, again, since it's a horizontal line, it's y equals, and that it's a number. How we find that number is we take a over c, positive a over positive c. Now, just to be clear, if this is negative, if this is like negative 2x plus 3, this is still going to be negative 2, okay? But it's not. We're not going to be changing any signs here. Whatever the signs are in a and c, that's what we're going to use. So the horizontal asymptote, y equals a over c. All right, so let's try a couple here. The directions are simple. Graph the function, state the domain, and range. Before we graph, let's start by identifying our asymptotes. Let's start with the horizontal asymptote. Horizontal asymptote. Okay, I'm just going to go asymptote. Okay, so horizontal, y equals. Let's figure out what we need to know. We need to know a over c. In this case, a is right there. It's the number in front of the top x, so that's going to be 2. C is the number in front of the bottom x, so that is 1. Okay, so we'll have a over c, which is 2 over 1, which then is 2. Okay, and then we need to do the vertical asymptote. So let's do that one, vertical asymptote. Okay, so that's x equals, and remember it's negative d over c. So remember d is the number on the bottom on its own, so we'll have negative, and then I'll make a fraction, so we'll have negative 3 over c. Again, that's this one here, that's 1. So we'll have negative 3, so negative 3, basically both become positive. We'll have 3 over 1, which is positive 3. So we have our vertical asymptote at 3, our horizontal asymptote at 2. So once we figure out those, let me bring in some graph paper here. So we slide this up just a touch. Okay, we'll draw in our x and y plane, x and y axis here. Okay, and we can go ahead and draw in our asymptotes. We know the horizontal asymptote is at 2, so that's right here. Our vertical asymptote is at 3, so that one is right here. So these are the two lines on our graph that our hyperbola is not going to intersect. Okay, let's figure out some x's and y's. Okay, so we'll have x, we'll have y. We'll just make 6 spaces. And let's see, the x value I want to avoid in this case is 3, because that's not going to work. So on the right-hand side, I'm going to go 4, 5, and 6. On the left side, I'm avoiding 3, so we'll go 2, 1, and 0. Okay? This is all stuff you can put in your graphing calculator. Just make sure when you do that you use parentheses around each side, the top and the bottom. Okay? So when you type this in, use your table to get your values. What you're going to find, for 0, you're going to get negative 1/3. For 1, you're going to get negative 1.5. For 2, will be negative 5. 3, let's see, not 3, 4 is going to be 9. 5 will be 5.5. And 6 gives you 4 and 1/3, or 4.3 repeating. Okay, so let's go ahead and plot these. I'm not going to be able to graph 4, 9 because I don't have enough room, but we'll be able to do the rest. So 0, negative 1/3 is about there. Okay, 1, negative 1.5 is in there. 2, negative 5, 2, 1, 2, 3, 4, 5. 2, negative 5 is right there. So we have our left side of the hyperbola. It looks something like this. Okay, now let's go ahead and fill in the right side. 4, 9, like I said, I'm not going to be able to graph that one because that's way up off the graph what I've got. 5, 5.5. So there's 3, 4, 5. 1, 2, 3, 4, 5.5 is right about in there. And then 6, 4.3 repeating. So 6, 2, 3, 4.3 somewhere in there. Now, knowing what this branch of the hyperbola looks like. I know that this one needs to look like this. So the way I graphed it in my note or on this video here, not a great picture because I didn't leave myself enough room to be able to show the entire branch of the hyperbola, but it has that general shape. So directions say graph the function, state the domain and range. Well, we've graphed it. Now we need to state the domain and range. I'll do that in green. So the domain, just like always with rational functions, the domain is going to be all real numbers except, now which x value don't we use? We skipped that x value of 3. So we're going to have all real numbers except 3. For the range, again, all real numbers except, now which y value is our asymptote? That would be a y value of 2. So our range is going to be all real numbers except 2. All right, let's try another one here. Let's scroll this up. Number 2, g of x is equal to 3x minus 1 over x plus 2. So let's start with let's go with the vertical asymptote this time. So vertical asymptote is x equals, remember it's negative d over c. So d and c, d is here, c is here. So we'll have negative d in this case is 2, c is 1. It's a number in front of x. So we'll have negative 2 over 1, which is just negative 2. Okay, let's do the horizontal asymptote, HA, horizontal asymptote, y equals, and we're going to have A over C. Okay, so my A value is 3, my C value is 1, 3 over 1, that would be 3. So my vertical asymptote is at negative 2, my horizontal asymptote is at positive 3. So when I make my XY plane here, and we'll just do it off to the side here. My vertical asymptote is going to be negative 2, so I'm actually going to shift my x-axis over a little bit, and I'm going to shift my y-axis, or sorry, my y-axis is over, my x-axis is going to go down. Okay, so then when I draw in my asymptotes, my vertical asymptote is at negative 2, my horizontal asymptote is at positive 3. Hopefully now we can see maybe a little more of this picture. We'll see. All right, so let's come up with some x's and y's. So get a table here, 6 spaces, 3, 4, 5, and 6. The x value I'm going to avoid this time is negative 2. So on the left side, I'm going to go negative 3, negative 4, negative 5. On the right side, I'm going to avoid negative 2, so we'll go negative 1, 0, and 1. Okay, again, this is all stuff you can put in your calculator as far as the equation in the y equals screen. Just type in numerator over denominator, make sure each part is in parentheses, and then get your table of values. So at negative 5, we're going to have a y value of 5 1/3. At negative 4, we had 6.5. At negative 3, we had a y value of 10. At negative 1, we got negative 4 in return. 0 gives us a y value of negative 1/2. And 1 gives us an answer of 2/3, or an output of 2/3. So let's plot these on the graph. I don't think I'm going to be able to get negative 3, positive 10, because 10 is way up there. Maybe we'll try to squeeze it in, but we'll just see how this goes. So let me slide this down just a touch, and we'll see if we can get to 10. So negative 5, 5 1/3. So we got 1, 2, 3, 4, 5, and then up to 5 1/3. There's 3, 4, 5, just a little bit higher. 4, 5, 3, 4, 5, and 1/3. Should be right in that general area. Negative 4, 6.5. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 and a half is about there. Negative 3, 10. So 6 and a half, 7, 8, 9, 10. We can't get it in. It's way up there. So we can kind of see the general shape of our hyperbola. The general shape of this branch looks like that. Okay. So now for the other side, negative 1, negative 4. So negative 1, negative 4 is way down there. 0, negative 1/2 is right there. Make that a little bigger. 1, 2/3, somewhere in this area. And we can draw in our next branch. So there is our general shape for the hyperbola. Now we need to talk about the domain and range of our function here. The domain, again, all real numbers. The range, also all real numbers, except which values? For the domain, which x value didn't I use? Well, if you look at our picture, if you look at the table, the x value I skipped was negative 2. So the domain is all real numbers except negative 2. The range, Which y value didn't I use? The horizontal asymptote is at 3, so that is the excluded value in the range. All real numbers except 3. All right, so there's a couple of examples of the, quote, advanced rational functions. Let's move on to something a little different. So rewriting rational functions, what this means is we're going from the advanced to the what you can call basic translated functions. How we're going to do that is by using polynomial long division. Okay, so that stuff in, I believe it was chapter 4, where we start dividing polynomials. It might have even been chapter 3, where we do synthetic division. That does come back. So if you don't remember that, I'm going to do it here for you in this video, but it might not be a bad idea to take a look back in your notes from the previous trimester to refresh your memory on polynomial long division. All right, so here's your example starting here. Example, rewrite g of x equals 2x plus 3 over x plus 1 in the form where we have just a single number over x minus h plus k. And then after that, we're going to graph the function, describe the graph of g as a transformation of the graph of f of x equals a over x. And so these two numbers, whenever we come up with, they will be the same. Okay? So let's get to it. So here we go. We are going to go with, we're going to rewrite g of x equals 2x plus 3 over x plus 1 in the form a over x minus h plus k. We're going to do that by doing polynomial long division. So think about a fraction. This is the top part, or this is what we're starting with, and we're dividing it by this. So the bottom part is your divisor. That's what goes on the outside of your division bracket. So I'm going to put x plus 1 on the outside of my bracket, and on the inside then goes 2x plus 3. Now, if you remember long division, we're going to take the biggest term, the highest degree term on the inside, and we'll divide it by the highest degree term on the outside. So we just, 2x divided by x leaves me with just 2. So I'm going to put a 2 above the constant term because it is a constant. So we'll have, and then once we do that, we're going to take 2 times x plus 1. So we'll take 2 times x, and that gives us 2x. And then we'll take 2 times 1, that gives us positive 2, and we are going to subtract. 2x minus 2x is 0, and I'm not going to write that. 3 minus positive 2 is positive 1. So now remember, we're done dividing once this degree is smaller than this degree. This is degree 0 because there is no x. It would be x to the 0 power. This is x to the first power. So we are done because, and also we're out of room up top. So what our answer is, we're going to have, how this usually would look, we would say g of x is equal to, if we were going to write the quotient, it would be 2 plus a remainder 1 over x plus 1, if you remember from polynomial long division. Now, normally we think when we're rewriting it in this form, all we need to do is switch these two around. So our actual answer is g of x is equal to 1 over x plus 1 plus 2. So this right here is your answer for the part where we rewrite it in the simpler form. Okay, once we've got this, now we can go ahead and graph the function. So I'm not even worried about the original one, this 2x plus 3 over x plus 1, because we now have it rewritten in a simpler form. Okay, so we know we're going to be using this g of x equals 1 over x plus 1 plus 2. So let's figure out where our asymptotes are. So we're going to have a horizontal asymptote, and we're also going to have a vertical asymptote. The vertical asymptote, remember, that deals with the horizontal translation, and it's always backwards with horizontal stuff, so plus 1 becomes x equals negative 1. Horizontal asymptote, that deals with the vertical translation. We went up 2, so then our horizontal asymptote is the line y equals positive 2. Okay, so when we graph, let me bring in some graph paper here. Let me draw an xy axis. There we go. So we can draw in our asymptotes. Y equals 2. Whoops. Let me get 2 dashes there. And x equals negative 1. So these are the two lines that our hyperbola is not going to cross. Okay? And then we can go ahead and come up with some x's and y's. So x, y, leave 6 spaces. And again, we can use our graphing calculators to come up with these y values once we figure out what x values we're looking for. The value we're going to avoid is negative 1. So on the right-hand side, I'm going to go 0, 1, and 2. On the left-hand side, then I'll go -2, -3, -4. We're avoiding the x value of -1. Okay? So again, type this in your graphing calculator. You can type in this, and then actually we'll just type in g of x, and just make sure x plus 1 is in parentheses, and then just use your table. So when you use your table, you get your y values. You're going to have 1.6 repeating for -4, and then 1.5 for -3. -2 gives you a y value of 1. 0 gives you a y value of 3. 1 gives you a y value of 2.5, and 2 results in 2.3 repeating. Okay, so let's go ahead and mark these on our graph. So -4, 1, 2, 3, 4, 1.6. 1.6 is right about in there. -3, 1.5 is there, very close together. -2, 1 is right in there. So our shape, it's kind of difficult to see here. It looks like this. Now that's not a very good drawing, but it has that general shape. Okay, so then let's do the other side. 0, 3 is right there. 1, 2.5 is there, and then 2, 2.3 repeating is right about in there. So then our other branch of our parabola, or hyperbola, not parabola, hyperbola, looks something like this. Okay, so what are our tasks? Rewrite g of x in the form a over x minus h plus k. We've done that. Graph the function. We've done that. Now we need to describe the graph of g as a transformation of the graph of f of x equals a over x. Basically what we're being asked to do here is tell we go from this, or we go actually from this to this. What changes? Well, we have this +1 on the underneath in the denominator, and we have the +2 on the outside. So what we can say to answer the last part of this, it's a transformation, or let's say this is the transformation. We'll just make a little statement here. Transformation. We can say this is a translation because we have the +1 on the denominator right next to x. It's a translation, 1 unit left and 2 units up because of the +2 on the end, 2 up of the graph of f of x equals, now what was a? Because it was a over x. So a in this case, in this example, is right there. It's going to be 1. Okay, so f of x equals 1 over x. Now, had we gotten something different, let's say this had been a 4, then we would say it's a translation, blah, 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 1 unit left, 2 units up of the graph of f of x equals whatever number this was. If it was 4, it'd be 4 over x. If it was 5, it'd be 5 over x. If it was -2, it'd be -2 over x. Okay? Whatever the number is in your new numerator, that's what's going to go in the numerator of your f of x. All right, last question here. A company purchases a blueprint plotter for $1,500. The plotter cost for each set of blueprints is $25. Question number 1. Estimate how many blueprints must be plotted for the average cost of the blueprints to fall to $75. Before we can do this, what I would suggest is figuring out how do we come up with an equation, because we're going to need an equation before we can estimate anything as far as cost. So total cost, so let's do this. So our average cost, how do we find average cost? Well, we take our total cost divided by the number of jobs, right? Number of jobs, or the number of plots, whatever you want to do, okay? So for the total cost, what all is involved in the total cost? Well, we have the cost to print, printing, plus the machine. Okay, we had to buy the machine. That is part of our total cost, machine. Okay, so can we come up with our equation? Well, how much does it cost to print or plot a set of blueprints? It tells us in the set, $25. Okay, 25. We don't know how many plots we're going to print, so we're going to say 25N, and I'm just using N for number of prints, plus how much is the machine? Well, it also tells that the machine costs $1,500. That is our expression for our total cost for printing these blueprints. Okay, so divided by the number of jobs. Well, how many jobs are we doing? We don't know. Okay, so we're just going to say N. That's going to tell us the average cost of plotting blueprints, okay? And we'll go from there. So the question then says, estimate how many blueprints must be plotted for the average cost of the blueprints to fall to $75. Okay, well what we need to do then is use our graphing calculator. Okay, so we're going to use our calculator and we're going to look for a Y value of 75. This is what gets typed into the calculator in the Y equals screen. Just make sure 25n plus 1500, and you'll have to use x, but make sure the numerator is in parentheses. And what we're going to do, we're going to look for the table, use the table to look for a Y value of 75. Okay, where that happens when you do that is right around an x value of 30. And I shouldn't say right around an x value of 30. It happens exactly at 30. So what we're going to say here for our answer is after or at 30 prints or 30 plots, the average cost is $75 per plot, because that's what it's asking us to say. Estimate how many blueprints must be plotted for the average cost of the blueprints to fall to $75. Because if you're scrolling through your table, what you're going to see is that the average cost, because that's the Y values, the average cost continues to drop the more plots you make, or the more plots you print for these blueprints. Okay, so question number 2 then, what happens to the average cost as the number of plots increases? Keep scrolling down your table. What you're going to notice is the cost is going to keep dropping, but it's not going to drop by as much as you print more and more prints. Rather than continuing to keep scrolling and keep scrolling and keep scrolling until we get our answer, what we can do is we can use this equation that we came up with, 25n plus 1500 over n, and figure out where the horizontal asymptote is, because horizontal asymptote deals with Y values. Okay, so this would be a, quote, advanced expression or equation. Okay, so we can find the horizontal asymptote. So I'm going to rewrite our expression or equation. C is equal to, our average cost is equal to 25n plus 1500 all over n. Now, to find the horizontal asymptote, because that's really what we're looking for, go back to green here. So we're looking for a horizontal asymptote. Okay, it's a Y equals, and remember from earlier, the horizontal asymptote in a advanced expression or equation is going to be Y equals A over C. So A in this case is 25. C in this case is the number in front of our variable in the bottom. That would be 1. So 25 over 1 is 25. So our horizontal asymptote occurs at 25. What this tells me, or what this tells you, is that as the number of plots increases, as the plots increase, or as we print more, then we can say that the average cost will be, or will approach $25. Is our average cost ever going to be exactly $25? No, it won't, because we're still going to have that original expense of $1,500 for the machine, but eventually we're going to be to the point where this cost is negligible. Ideally, we'd want millions of prints on the same machine, so then really this is the only cost that's going to matter. Okay, $25 per print, because at that point we've spread out that cost of the machine so far that it really isn't going to affect the cost of one print. So what we can say is as plots increase, the average cost will approach $25. We'll never get there exactly, but we'll get awfully close, especially as you continue printing and make more and more and more plots.